This is the second set of slides covering two topics from Harry's textbook, chapter Fundamentals of Electrochemistry. Here we'll cover Nernst equation and we'll briefly look at biochemist's use of potential. Please read these two topics in your book. Now, free energy is related to the standard free energy change according to this equation. Delta G equals delta G0 plus RT natural logarithm of Q, where Q is reaction quotient. For this, see your general chemistry textbook as chapter on free energy. Now, from the previous slide set, we learned that delta G for electrical processes is minus N Fe. Let's replace delta G in equation 1 with minus NFE from 2. Minus NFE equals delta G plus RT ln Q. Now let's divide both sides by minus NF. We are getting such an equation and we'll continue on the next slide. Here, delta G0, N, and F are constant number for any specific reaction. Let's write E0 for this constant. Then, because we are dividing by minus NF, plus will be replaced by minus. The resulting equation is known as Nernst equation. E equal E0, some constant, minus RT divided by NF ln Q, where Q is reaction quotient. Again, the same reaction. What is Q? We write all half reactions as reductions. So oxidated state plus number of electrons to reduced state. Then Q will be concentrations of all products at the right side divided by concentrations of all reactants on the left side. Next simplification. We usually work at room temperature. At room temperature, RT divided by F will be approximately equal to 59 millivolts after switching from natural logarithm to more convenient decimal. So the equation for practical use can be written as potential equals to E0 minus some coefficient close to 0.06 volts divided by number of electrons and multiply by decimal log of Q. This is a good practical approximation for many cases. Now let's look at several examples. First, we have a beaker in which there is iron 3 plus salt and iron 2 plus salt. So there are Fe3 plus and Fe2 plus ions. Now there is platinum electrode immersed in that solution, and there is connection by bridge to some reference electrode, some other wire. In general, E equals E0 minus 0.06 divided by N log Q. Now what's N in our case? In our reaction, only one electron is involved, so N is equal to 1. Reaction quotient will be concentration of everything on reduced side, that is concentration of Fe2 plus ion, divided by concentration of everything on oxidated side, which is concentration of Fe3 plus ions. Now E0 is known from reference book. In our case we can take it from Harris. It's 0.77 volts. So our Nernst equation for this system would be E equals 0.77 volts plus 0.06 volts multiplied by log of ratio concentrations of Fe3 plus divided by concentration of Fe2 plus. Next example. A silver electrode. This is the electrode we were using in our titration of chloride ion. Let's put silver wire in solution of silver ions. Again, we have the same Nernst equation for general case, but our redox reaction is Ag plus 1 electron making metal silver. Concentration of our product is molar fraction of silver in pure silver, which is 1. You have pure silver in pure silver. It's constant, it's 1. Now our reactants is silver ion in solution. So it will be molarity of silver ions in solution. Now E0, again from the reference book or from Harris, is 0.80 volts. So the resulting equation will be potential equal to 0.80 volts plus 0.06 volts multiplied by a log of silver ions molarity. This is so-called first type electrode. We have plus sign before log of concentration. Third example. Let's put silver wire covered with solid silver chloride into solution of chloride ion. Now our reaction is different from the previous one. We have AgCl solid taking 1 electron, making Ag, that is silver, metal solid, and chloride ions in solution. In this case, above the line will be molar fraction of silver in silver wire. That's 1. Then molarity of chloride ions. Below the line we'll have molar fraction of silver chloride in pure silver chloride, which is 1 again. So we can write Nernst equation using E0 0.22 volts, again taken from Harris, and now minus 0.06 decimal log of chloride ion concentration. We have minus sign before second term. This is so-called second type electrode because we have minus sign and it's responsible for negative ions. Now, biochemists use slightly different E0 because the pH inside plant of any or animal is about 7. Reduction that is applied to pH 0 are not convenient. For example, at pH 7, ascorbic acid is much more powerful reducing agent than succinic However, at 7, the order is reversed. What is relevant is reducing strength at pH 7, not at pH 0. Standard potential for redox reaction is defined for cell in which all activities are unity. Formal potential is the reduction potential that applies for specified set of conditions, say pH, different ionic strengths, some concentration of complexing agent. Biochemists call this formal potential at pH 7 E0 prime. In this table, we can see E0 primes for some important biological couples. Here is our ascorbic acid, vitamin C. Vitamin C can be oxidized to dehydroascorbic acid, slightly different, which is not acid at all. But ascorbic acid has two protons that are acidic. When we look at formal potential as a function of pH, it's obviously not a constant. It's a steep curve that changes until reaching pK2, which is 11.79. Above this pK2, so above pH 12, there is no protons involved in redox reaction, and potential becomes independent of pH. This highlights how important it is to know pH when you study biological systems.